Hello and welcome to another power system analysis class. In the previous class, we spoke about transmission line parameters, transmission line resistance, transmission line inductance, capacitance, and so on, and how we bundle transmission lines. Today, we're going to start with power transfer and how we can maximize power transfer. It's going to be a little bit of explanation on that. And then we're going to start with transformers, which is a major component of power systems. We will start with ideal transformers. We're gonna solve a problem. After that, we're gonna have a short quiz and we will start with non-ideal transformers. Before I start, do you have any questions from the previous class or exam? No? Okay. So first, we're going to start with power transfer in short lines. The main goal here is to maximize power transfer. And to maximize power transfer, meaning that the power that we generate is going to be near the power or exactly equal to the power of the load side. And we are mostly interested in real power because, as mentioned, reactive power is a type of waste in our system. So we want to, when we say maximizing the power transfer, we are interested in maximizing the real power transfer. And this is an example and the way that we calculate that. On the left side, we have the source, V1, I1, S12 is given to the source, and V2 is our load. And in between, we have the transmission line with the impedance of Z. Now, the parent power, S12, would be V1, I1 conjugate. And I can write I1 conjugate. I can use the Ohm's law for that, which is going to be V over Z. In other words, it's going to be V1 minus V2 over Z. Now, in a polar form, V1 is V1, the magnitude of the V1 with a degree of theta 1, and V2 is V2, the magnitude of that with the degree of theta 2. And Z is going to be the magnitude of Z with the degree of theta Z. Now, if we multiply V1 and we replace this with the polar form, it's going to be V1 times V1 or V1 squared over Z with the degree of theta Z, and then V1 V2, and by the way, negative, minus V1 V2 over Z with the degree of theta Z plus theta 1, 2. Now, if we assume that the transmission line is lossless with the impedance of Jx, and we are again interested in only measuring real power losses in the system. We know that apparent power S is P plus JQ, or real power plus the reactive power. And if we do that, let me bring up my pen. So S12 is going to be P12 plus JQ12. Now, which is going to be V1 square over Z, degree of 90 degree, minus V1 V2 over Z, degree of 90 degree plus theta 1, 2. And since negative cosine of 90 degrees plus theta 1, 2 is equal to sine of 1, 2, we get, and again, we're only interested in P. So P12 would be V1 V2 over X sine of theta 1, 2. And hence the maximum power transfer is going to be equal to V1 V2 over X. Now, if V1 and V2 are equal, then we're going to have V1 squared over X, which is going to give us the maximum power transfer. But obviously V2 is going to be less because we have loss. We don't have a lossless system in the system. So we're going to have less than the maximum that we're going to have. Now, some limits that affect power transfer, first of all, is the limits due to heating of conductors. And we already discussed this. When you have a resistance in the transfer line and transmission lines, that resistance creates heat, translates to heat. And what happens when you heat up metal? You're going to soften it. You're going to have a sagging effect. And this also depends heavily on ambient conditions. Obviously, if your transmission line is in Canada, it's going to have different characteristics than what you have in, for example, Houston. For many lines, sagging is a limiting constraint, as mentioned, but there are newer lines like the 3M 2004 ORNL from 3M that has like a ceramic Nixle fiber core, and these can operate up to 200 degrees Celsius, which is, it's going to technically, burn anything around it. So there's another problem. You have a line that's technically a heater, 200-degree heater, and if you have a tree or anything, contacting that is going to immediately start a fire. That's the problem that we had, and we saw a lot in California, especially during dry seasons. A lot of the fires were caused by not maintaining these transmission lines and transformers, and they caused a lot of fires. So trees grow and will eventually hit lines if they are planted under the lines, or even you have a forest and you're passing the line. That's one reason that we have these high voltage transmission lines very high up ground, because we don't want them to contact any trees. Now, another limit affecting power transfer is going to be the angle limit. The maximum power transfer occurs when the line angle difference is 90 degrees. Using this equation, what is the sine of 90 degrees? It's what? 1. Thank you so much. So this maximum occurs when this is the theta 1, 2 is 90 degrees. And then you have a maximum. So another problem that we're going to have is the angle difference. And this actual limit is substantially less due to multiple lines in the system, meaning it's going to be less than 90 degrees. And what we have to do, we have to use different methods to compensate for the power and for the angle as well. And we have voltage stability limits as well. As power transfer increases, reactive losses also increase as a factor of I square X, and that has a cascading effect, because as reactance power increases, the voltage falls, resulting in a potentially cascading voltage collapse in the system. So in the exam, if we ask about the limits affecting power transfer, 1, thermal limits, because of the resistance of the line sagging. Number 2, angle limits. And number 3, voltage stability limits, which is from the reactive or reactance that we have in the system. So we have 3 major limiting factors that affect power transfer. Now, this example shows a power system from generation to load. As you know, again, the circle indicates the generation and the arrow is the load. And the generation is generating 9,000 megawatts and negative 2,912 megavolt amp reactive. And you can see how much voltage is given to the grid or transmission line at 765 kilovolts at 0 degrees. But after the first transformer, for example, that increases to 816, and we have a negative 11.4 degree. And in the next, the voltage drops, increases to 847, and the angle is negative 19.5 degrees. And finally, it's 857 with a degree of negative 27.3 degrees. Now, you can see here that in the load, we have the power is 9,000 megawatts, and the reactive power is 0 megavolt amp reactive. This is for an ideal situation, never this happens. But how did we get 0 megavolt amp reactives? Because of the phase shifts or the angles that we have. If this was 0 and we wanted to get 0 out, then we had to add capacitors or power factor angle compensators to do that. Now, this shows transmission line series compensation. How do we do compensation again? Using capacitor banks. So one way to increase the transmission capacity of a transmission line that is limited by the reactance is to add series compensation, which are large capacitor banks. So capacitors are usually placed in series with the transmission line. And you can see here an example of that. We usually put them in a way that it could be bypassed because the power generation and the load fluctuates. You have peak hours and off-peak hours, light demand and high demand, and you want to be able to control that reactive power and compensators as well. Now, for transmission line series compensation, the amount of series compensation is expressed as a percentage of the total line reactance. For example, we say we are compensating at 50% of the reactance. But usually this number, we want it to be close to 100. The series capacitance is usually set up so that it can be bypassed sometimes. The reason is there can be excessive reactive power generation on the system during light loads, like at night when we have low demand. So when you have lower demand, you have high powers on the lines, higher reactive, and you need a bigger capacitor bank or capacitance compensation. There can be a concern with subsynchronous interactions or SSIs, and I'll explain more about this later. Fn is 1 over square root of LC. In other words, if not square root of XC over XL. So the frequency again depends on the reactive, the inductance and the capacitance that we have in the system. Now, this is an example of another transmission line. You have a generator generating 2200 megawatts with negative 0.2 megavolt amp reactive. It's giving 765 kilowatts to the transmission line. The line angle difference is negative 21.4 degrees. And then you have a capacitor bank at the end, and that capacitor bank at the end compensates for the reactive power and reduces that to 0. Again, this is an ideal. We will never transmit the same amount of real power. We're not going to have that in the generation and also the load side. Now that we learned about the limits, the transfer limits, which are, again, the transfer limits that we have from the resistance, which creates heat, the limits that we have from angle, which is reactive power, and the limitations that we have from the inductance in the system, again, which we have to use power factor compensators in the system. Now, we're going to start with transformers. Some basic rules of transformers. They could range from few volts to few 100,000 volts. In electronics and your lab, if you had a lab with me, we saw we had a normal transformer was like a 24 to 120 or 12 to 120 and or 120 to 12, and it could go up to 700,000 volts, which is a huge amount. Transformers are used to transfer power between different voltage levels. The ability to inexpensively change voltage levels is a key advantage of a AC system over DC, and that's the reason AC won the current wars in the early 1900s, because you can easily and very cheap, increase the voltage and reduce the power loss. In this section, we will develop models for transformer and discuss various ways of connecting three-phase transformers. Again, you can read faster. Before I start with the modeling and getting into the math, I want to show you the physical part and how a transformer looks like. Usually, the primary side, we have a primary side, and the secondary side, we also show it with, V1 and V2, or VP and VS. V1 being the primary side and VS being the second. VS is secondary, or the V2. We showed with that as well. You've all seen transformers. This is a 115 to 35 kilovolt distribution transformer. On the system, you can see the LTC. You can see the important part is the radiation with the fans. The radiation, usually you have oil in it. You may think that this distribution and transformers don't require maintenance. The transmission line itself requires minimal maintenance. The main maintenance is in these transformers. It's like a car. You have to change the oil every, 200,000, depending on what oil and what type of transformer are there. If you don't change the oil, it's gonna lose its viscosity and get thickened like grease thing, and it can't. The oil is a medium to cool down the system, and it's also, some of the transformers are dipped into the oil, and that oil actually acts like a insulator as well. And sometimes you have a circulating oiling system. They have a pump, some of them, like very high voltage ones. And they have filters, so if you have debris in that, it's going to block it, it's going to get hot, and it's going to damage the whole system. So regular maintenance, you need to have it in transformer. It's not like a car. Every 5, 10 years, sometimes 20 years, you have to do regular maintenance. And depending on the weather, if it's in a cold weather, high climate, you need different type of oils. Now, this shows it from a different angle, a different device. This is a 230 kilovolt system. And you can see the surge arresters, and you can see the oil cooler and the radiation fans. And this one has an active cooling system with fans. This is for very high voltage system. Usually in 5 kilovolts, you don't see active cooling because, again, it's going to consume a lot of power. And here you can see the oil pump. Again, if this oil pump, you don't maintain it, it's going to break down. You're going to have a huge problem. It's not like a normal transformer that is going to, sometimes these things explode if you have too much heat. It's going to just evaporate all the oil. It's a very dangerous thing. That's the reason they have redundancy. They have a couple of oil pumps, and they have a fail system that it will cut off power if the temperature gets too hot. Anyway, one thing that I wanted you to see is, do you know what these rims are? These coin shapes are perfect insulators. And why are they like this? Does anyone know? Does anyone know why they are built like this? Have you ever thought why we build them like this? There's a very smart engineering actually behind this. And I have a video. I'm sorry. Yeah, this one is. If you get these mixed up, you're going to have some problems. So you can see there's smart, design, but depending on how much voltage you need different bushings. So if it's you saw in the previous one, the bushings are different, the shape, the size, everything is going to be different for them. Now, for modeling a transformer, we would first start with an ideal transformer, as we do for any other circuit. We start with ideal components. And for an ideal transformer, first we want to find the current voltage relationship between the primary and the secondary side. And we have some assumptions. First, we have no real power loss. And second is that the magnetic core has infinite permeability, and we have no leaking flux. And I'll explain more about that. And we usually, in a transformer, the primary side is the side that usually takes the power, and the secondary side is the side that usually delivers the power. So primary side could be the generator, and the secondary side could be the grid, or the primary side could be the grid, and the secondary side would be the load or your home. Primary side is usually not, if it's connected to the generator, it's opposite. Usually the side with the higher voltage, and the secondary is the one with the lower voltage. So it's a step down. By the way, if we reduce the voltage, it's going to be step down. If you increase it, meaning the secondary volt is greater than the primary, it's a step up transformer. It's called a step up. But if it's connected to the generator, it's usually a step up, because we want to step up the voltage at the generator side and step down at the load side. Now, based on these assumptions, we would draw the transformer graph for an ideal transformer. So we have the primary side, V1 or Vp, and the primary voltage and current. And as you know, when you put a current through a wire, you create a magnetic flux. And since we assume that we have infinite permeability, meaning we have no magnetic resistance, in other words, meaning all these magnetic flux that is generated from the primary side would be converted to the secondary side. We have no loss in the system. So assume we have flux phi m in magnetic material, and we have no loss in the system and no eddy current and so on. Then lambda 1 would be equal to m1 phi m, which is the magnetic field created by that. And that goes through the core and translates to lambda 2, which is going to be n2 phi m. Again, phi m is shared because we have no loss. Now v1 would be d lambda 1 over dt, which is going to be n1 d phi m over dt, and v2 is going to be d lambda 2 over dt, which is n2 d phi m over dt. d phi and d phi, these two are equal to each other. So d phi m over dt is going to be v1 over n1, which is going to be equal to v2 over n2. Therefore, we can write it at the following. v1 over v2 is n1 over n2, and n1 over n2 is called A, which is our turns ratio. You can write this down because we're going to solve a few problems with this. You already know this. It's a pretty simple equation. v1 over v2, or we can write it like this as well. vp over vs is going to be equal to np over ns, which is equal to A, or the turn ratio. Now, That's the relation for the voltage. For the current, we can do the same thing. To get the current relationship, we use the Ampere's law. MMF is the integral over the close, and this is the close of H dot dl, which is going to be N1 I1 plus N2 I prime 2. H times length gives us N1 I1 plus N2 I2 prime. You learned this from physics magnetics. And B times length over mu is going to be equal to N1 I1 plus N2 I prime 2. Now, assuming uniform flux density in the core, phi times the length over mu times the area gives us N1 I1 plus N2 I prime 2. If mu is infinite, as we assumed, permeability, then 0 would be equal to, because it's going to be the length divided by an infinite, which gives us 0. Which would be equal to 0 is equal to N1 I1 plus N2 I prime 2. And therefore, if we simplify that, I1 over I2 gives us N2 over N1 or 1 over A. So with the same ratio that we increase the voltage, we reduce the current. Therefore, P1 is equal to P2. We don't have any loss in the system, or the primary power is equal to the secondary power. V1 I1 is equal to V2 I2. Now we can use this matrix, and this is the way that we represent a transformer, and this shows the direction of the current and the turn ratio N1, N2. And for this one particular case, A is equal to 1, meaning N1 is equal to N2. We have the primary voltage and current and secondary voltage and current. And we can use a matrix to write it. So it's going to be V1 I1 would be as A and 0 and 0 and 1 over A, V2 over I2. Now, if we want to find the impedance, we can use this equation to find the impedance. We know that impedance using Ohm's law. Okay. Z, Ohm's law, is going to be equal to V over I, or V is equal to IR. Now, from that, we can find the secondary impedance, and we can transfer that to the primary side. So we know that V1 is equal to A V2, and I1 is equal to 1 over A V2 over Z. Now V1 over I1 gives us Z1, which is equal to A square Z. So if I want to transfer the impedance from the secondary winding to the primary, I have to multiply it by A square. I want you to write this down as well. So transferring the impedance from the secondary side to the primary side, you have to multiply it by the turn ratio, the power of 2. Now, let's solve an example. An ideal transformer has a primary voltage of 240 volts. The primary turn and there is to the secondary turn ratio is 4:1. And the load resistance is 15 ohms. We want to find the secondary voltage Vs, the secondary current Is, the primary current Ip, the input impedance Zn, and finally the input-output power. I'll give you a few minutes to think on this, and then I would solve it. Okay. So the first one and the second one would be as a quiz. Now, we know that V primary over V secondary, or V1 over V2, is equal to NP over NS, which is equal to 4. So Vs would be equal to primary, which is 240, divided by 4, which would give us 60 volts. So the secondary voltage is 60 volts. Now, what is the relation for I secondary over I primary is also equal to NP over NS. Now, how can I find the secondary current? Thank you. It's going to be V secondary over R load. By the way, let me draw this on top of here, so it gives you a better picture. This is 15 ohms. It's your RL. This is 4:1 ratio. And the input voltage is 240 volts, and we don't have the output voltage. So if I get this at 60 volts, I can find its current. So it's going to be 60 divided by 15 gives us 4 amps. So I know that IS is 4 amps. Now I want to find the primary current, IP. So 4 divided by IP is equal to NP over NS, which is 4. Okay? Therefore, IP would be equal to what? Thank you. 1 amp. So this is 1 amp. Now, what about this input impedance? Now, Z input is going to be equal to A square times ZL, which is going to be, what is A? It's 4, the power of 2, times ZL is 15. So it's going to be 16 times 15 gives us 10, 24, thank you, 240 ohms. So this is 240 ohms. Now we want to find the input and the output power. The secondary or the output power is going to be VS IS. Now what is VS? It's 60. What is IS? It's 4. So it gives us 240 watts. Now what about the primary power or input power? It's going to be V primary, I primary, which gives us, again, 240 because the input voltage was 240. And what was the input current? 1. This is IP. So it gives us 240 watts. So you can see, because we have no loss, primary and the secondary power are equal.
When you're reflecting from secondary to the primary, it's split.
Yes, for the impedance, yes. So if you want to model it and you have multiple, that's a great question. And let me give you an example on that. Okay, I'll give you an example on it in a few seconds. First, I want you to solve this quiz, and I'll give you an example of having multiple transformers in it and transferring the. Okay, so quiz. We have an ideal transformer with the following parameters. Vs is 120 volts, Np is equal to Ns, and the ratio is 6:1. RL is 10 ohms, and we want to find, again, primary voltage, secondary current, primary current, input impedance, so on.
That's 10 ohms.
Yes, 10 ohms. No, keep it. I want to give another quiz. Thank you for bringing that question. I'll give you an example of that as well. So imagine we have three, or that makes it, let's make it two transformers. So imagine we have a two transformer system, three transformer. And for the third transformer, ZL is 8. Let's make it a complex number plus J 6 ohms. So I would solve a complex number as well. And then we have, this is transformer number 2. This is transformer number 1. Let's say. So I have two transformers. The ratio for the first transformer, N1, N2, is 4:1. Okay, so the first one is 4:1. And for N3, N4, it's 3:1. Okay. Now, we want to find the equivalent impedance refer to the input of transformer 1. So what is Z input? Again, the equation is going to be Z is N primary or over NS or A square ZL. I'll give you, let's say, 5 to 10 minutes, and it's going to be, this is your second quiz number question. I think it's correct. I haven't solved it yet myself. Thank you. Have you all solved it? Okay. So first step is to move this to the first transformer. Let me do it with a different color. And for that, Z, if we want to move to the output of the second to the first, it's going to be equal to NP over N square, NS square times ZL, which gives us, this is for Z going to ZL1. This is ZL2. It will be, what is the second? Oh, this one is 3-to-1. So it's going to be 3-to-1 times 8 plus J6 ohms. So 3 times, and this is, I'm sorry, square. So it's going to be 9 times 8. Yes, plus J6 ohms, which gives us 72 plus J54 ohms. Now, this is going to be ZT2 of my primary side. And if I want to find ZT1, this makes it this 2, and this makes this 3, and I want to find Z1, Zn. It would be, again, NP over NS square ZL2, which this time it's 4-to-1 square times 72 plus J54 ohms. So it's going to be 16 times 72. What did you get? 1,152. Yes, plus 16 times 554, 10, 54, 540. Yes, 864. J 860. So this gives us a very good picture on what a big impact a small load resistance has on the input. When it's transferred and you have multiple, transformers, then a 8 ohm resistor is pretty low, becomes a 1 kilo ohm resistor, which is pretty high in a transmission system. So this is 1,152 plus J 864 ohms. Is it clear? Yes? Okay. And let me write down the model as well that we had for the second one. So when we converted it to the first transformer, this was now 72 plus J 54 ohms. And this was 4-to-1. Okay. Now, we discussed ideal transformer, but obviously in real world, real transformers don't have ideal parameters. They have losses in both the core, and you have loss in the copper as well. So that's a problem. You also have leakage flux. Not all the flux goes through the core. Some of them go through the air and dissipates. And you have finite permeability of magnetic core. And for real power loss, resistance in windings are I square R. And we have core losses due to eddy currents and hysteresis. Now, eddy currents arise because of changing flux in core. Eddy currents can be reduced by laminating the core. That's the reason you see that transformer cores are laminated, like thin sheets of plates just connected to each other. And I'll explain what the effect of that is. Sometimes eddy current is actually good. If you have a electric kettle, electric pot or something that you want to boil water or something, we use actually eddy current to heat up the system quickly. So any magnetic heater, eddy current is good there. And so eddy current generates a lot of heat, and it's just dissipated. On the left side, you see a core with no lamination, and we have high eddy current. And on the right, with lamination, you have very low eddy currents, which is much less the one on the right, on the left. But it makes building the core much more complicated and expensive, building it from a single block than building it from multiple sheets and connecting them together. Now, another type of loss is the hysteresis losses. These are proportional to area of BH curve and the frequency. These losses are reduced by using materials with a thin BH curve. Now, why does this occur? If you have a nail, I don't know if you have this experience, or a screwdriver and put a wire around it, put a magnetic field for like a few minutes out of it. When you disconnect the current, what happens to the core? It stays magnetic. That's the reason we have this hysteresis law. Means when you put a magnetic field through the core and you disconnect that current, the core is now magnetic. Now, when you have a alternating current, meaning you're changing the direction of the magnetic field 50 times per second or 60 times per second, depending on the frequency. But the thing is, if the magnetic field, so for example, if I have a core that goes like this and the current is this way, what happens is now have a magnetic field which is this way. Now, if the direction of the current suddenly changes because you have an AC current, then the magnetic field is changing. But the thing is, the first magnetic field that you created caused the core to have a magnetic field going upwards, okay? Now, the second magnetic field should overcome the first one first and then reverse it. And then the third one should overcome the second one. You know what I mean? So this creates a problem because now you're just, competing with the previous magnetic field. If that hysteresis is large, meaning the area inside this is large, you're going to have a lot of loss in the system. It generates heat. It creates a lot of problem. So we want a system that has the smallest hysteresis possible, something very thin. Something that looks like this. The thinner that is, meaning we have less hysteresis in the system. Now, how can we do that? There are some alloys that we add to the core that reduces this hysteresis. Sometimes it's good when we want to increase that. I don't know if you've seen some of these screwdrivers. They have like magnetics at the tip so you can pick up a screw. Those actually, they go through a process, and those materials are made out of a type of material that we actually like to have this hysteresis because we want to make a magnetic material out of a steel core, So sometimes we want to add to that. If you want to build a motor, for example, sometimes it's beneficial. And that's where rare earth materials, come in as well. They create some type of, alloys that it creates these hysteresis, and you have a better magnetic field. Sometimes we want to reduce it, sometimes we want to increase it, depending on the application. Yes?
Laminations, these cores, laminations, do they need to be?
No, they don't need to be insulated. No. That's a great question, by the way. I wanted to, but most of the time you don't need to even, so I can rip them apart and you would see it's just laminated. It's just break. It's just piece of sheets, and sometimes to keep them together, they put glue between them. I've seen that, but most of the time, or a type of oil, but no, it's necessary. No. Depends on your application, but not necessary. Actually, you don't want to put insulator, because if you put insulator, then you interrupt the magnetic flux. You want still the magnetic field to go through them, but you don't want to have the eddy current. Okay, so there's nothing between. Thank you for bringing up that question, by the way. I wanted to mention that and I forgot. Thank you. Now, I think it's enough up to today because for this point, because if I start this, I don't have enough time to finish this. So next class, we would start the with the non-ideal transformer, different parameters, and the modeling of a non-ideal transformer. Again, next week we have our spring break, so we won't have any class and I won't post any videos as well. Thank you so much and have a great day.